importante para esta jornada durante toda esta semana. Vamos a comenzar saludando también a todos los que se encuentran conectados con nosotros a través del canal de Edumedios de la UPTC. Los invitamos a que nos pongamos de pie, vamos a entonar el himno de nuestra Universidad Pedagógica y Tecnológica de Colombia. Todos de pie, por favor. Nos acompaña para la apertura de nuestro acto protocolario, de nuestro evento, el doctor Carlos Mauricio Moreno Telles, vicerrector de Investigación y Extensión, la señora directora de Investigaciones de la UPTC, la doctora Yolanda Torres Pérez, la decana de la Facultad de Ciencias, doctora Irina Tatiana Morales Castaño, la directora del Centro de Gestión de Investigación y Extensión de la Facultad de Ciencias, la doctora Judith Elena Ojeda Silva, el doctor Héctor Suárez, el director de posgrados de la Facultad de Ciencias, y por supuesto le damos un saludo muy especial a nuestro conferencista internacional, el doctor Samuel López, que nos va a acompañar en unos minutos y estará con nosotros. A todos los docentes, a nuestros estudiantes invitados también les presentamos la más cordial bienvenida. Invitamos para nuestras palabras de apertura a la señora directora del Centro de Gestión de Investigación y Extensión de la Facultad de Ciencias, la doctora Judith Elena Ojeda Silva.
Muchas gracias. Buenos días a todos. Buenos días a la mesa directiva, a estudiantes, a profesores, a egresados. Es para mí un gran honor como directora del Centro de Gestión de Investigación y Extensión CIEC de la Facultad de Ciencias de la UPTC, darles la más cordial bienvenida al 7º Encuentro Internacional de la Facultad de Ciencias INFAS 2024. Este encuentro, que con orgullo celebramos cada año desde su creación en el 2006 y de manera internacional desde el 2018, se ha convertido en un pilar para fomentar la colaboración académica y avanzar en el conocimiento científico dentro de nuestra comunidad. Hoy nos reunimos no solo para compartir los resultados destacados de nuestras investigaciones, sino también para explorar nuevas vías de innovación y descubrimiento. El tema central de este año, enfocado en la integración de la inteligencia artificial en las ciencias básicas, tiene un significado especial para nosotros. La inteligencia artificial está transformando la forma en abordar la investigación. Su capacidad para procesar enormes cantidades de datos, identificar patrones y predecir resultados nos permite lograr avances que antes eran inimaginables. Ya sea en física, química, biología o matemáticas, el impacto de la inteligencia artificial es innegable y es nuestra responsabilidad como científicos aprovechar su poder para bienestar de la sociedad. El programa de este año abarca 6 emocionantes áreas temáticas: la integración de la inteligencia artificial, modelos y simulación, ciencia de materiales, nanociencia, enfoques innovadores a la enseñanza de las ciencias. Todas estas áreas son vitales para nuestras disciplinas y también son críticas para enfrentar los desafíos apremiantes de nuestro tiempo, ya sea mediante el desarrollo de soluciones energéticas sostenibles, el descubrimiento de nuevos materiales o la mejora como enseñamos e inspiramos a las próximas generaciones de científicos. La participación de los grupos de investigación de nuestra facultad, que abarca ciencias biológicas, físicas, químicas y matemáticas, y estudios de posgrado, demuestra el compromiso de la UPTC y del CIEC en la construcción de un entorno académico y dinámico. Siempre hemos trabajado para fomentar la investigación y la apropiación social del conocimiento. A medida que avanzamos, sigamos fortaleciendo los lazos que hemos creado como investigadores nacionales e internacionales, expandiendo las redes que impulsarán nuestro trabajo hacia el futuro. Les invito a que se sumerjan en las presentaciones, discusiones e intercambios en estos días, sabiendo que cada uno de ustedes desempeña un papel vital en el avance de la ciencia y la tecnología para beneficio de todos. Una vez más, bienvenidos al INFAS 2024. Estoy segura de que de este encuentro surgirán contribuciones, colaboraciones y muy emocionantes. Muchas gracias.
Muchas gracias. A continuación, escuchemos con atención a la señora decana de la Facultad de Ciencias, doctora Irina Tatiana Morales Castaño.
Buenos días a todos los presentes, a las directivas de la UPTC, invitados internacionales, nacionales, investigadores y estudiantes. Reciban un cordial saludo desde la decanatura de la Facultad de Ciencias. La decanatura se complace en participar del 7º Encuentro Internacional de la Facultad de Ciencias, enmarcado en el 28ª Jornada Internacional de Investigación y Extensión de la UPTC, la cual se realiza con apoyo activo de grupos de investigación, jóvenes investigadores y semilleros de investigación de los programas de Biología, Física, Matemáticas y Estadística y Química, y de los posgrados en Ciencias de nuestra facultad. Como lo indica el lema de nuestro encuentro, hacia una nueva era de la inteligencia artificial en la ciencia del mañana, se trabajarán diferentes ejes temáticos. En un mundo cada vez más complejo, la inteligencia artificial emerge como una fuerza transformadora. Desde el descubrimiento de nuevos fármacos hasta la predicción de fenómenos climáticos extremos, la inteligencia artificial está revolucionando la forma en que abordamos los desafíos científicos más apremiantes. En este 7º Encuentro Internacional exploraremos cómo la tecnología está redefiniendo disciplinas como la biología, la física, las matemáticas y la química. Al fomentar la interdisciplinariedad, buscamos impulsar la innovación y descubrir nuevas soluciones para los problemas más urgentes de nuestra sociedad. Este evento reunirá a destacados investigadores nacionales e internacionales, quienes compartirán sus conocimientos en conferencias magistrales y ponencias especializadas. Además de presentaciones orales y de póster, ofreceremos actividades para todos los públicos, desde una sesión especial para despertar la curiosidad científica en los más jóvenes, titulado Explorando la vida secreta de los insectos, hasta un conversatorio sobre las tendencias más recientes en inteligencia artificial. Este encuentro fomenta la generación de nuevo conocimiento a través de la participación activa de toda nuestra comunidad académica, desde estudiantes de pregrado hasta egresados. Todos tienen la oportunidad de compartir sus investigaciones y establecer colaboraciones. Además, el 7º Encuentro de Graduados de posgrados de la Facultad de Ciencias nos permitirá fortalecer los lazos con nuestros exalumnos. Quiero expresar mi sincero agradecimiento al comité organizador de este importante evento, en cabeza de la doctora Judith Ojeda, directora del CIEC, Catalina, Clarita, Margot, Omaida, Nelsi, Paola, Héctor, José Mauricio y demás integrantes del comité, quienes dedicaron varias horas de su tiempo y pusieron empeño en la preparación de este evento. Agradezco además el apoyo del vicerrector Carlos Mauricio y la directora de Investigaciones Yolanda, así como la valiosa contribución de jóvenes investigadores, semilleros y docentes. Este evento será una oportunidad única para discutir las últimas tendencias en inteligencia artificial y su impacto en las ciencias básicas. Estoy segura de que las ideas y conexiones establecidas aquí inspirarán futuras investigaciones y colaboraciones. Así que, como dijo Marie Curie, nada en la vida debe ser temido, solo entendido. Les invito a seguir aprendiendo, explorando y entendiendo el mundo que nos rodea. Les invito a seguir explorando nuevas fronteras en la ciencia. Muchos éxitos en la jornada.
Muchas gracias. Y antes de dar paso a nuestro conferencista internacional, escuchemos con atención al señor vicerrector de Investigación y Extensión, el doctor Carlos Mauricio Moreno Telles.
Muy buenos días a todas, a todos. Un saludo muy especial a la mesa principal, pero indiscutiblemente un saludo a nuestros investigadores, a nuestros invitados internacionales, a los profesores, investigadores y a toda la comunidad estudiantil que está hoy presente. La verdad, estamos muy contentos. Todo lo posible para sacar adelante un evento tan importante como esto. Me alegra muchísimo ver tantos estudiantes, tanta gente joven, quienes van a ser indudablemente el futuro de las investigaciones que manejamos desde nuestra facultad. Les deseo a todos en esta jornada, en estos días, un éxito, que sea muy productivo, muy provechoso el aprendizaje que nuestros investigadores nos vienen a compartir y que nosotros también como territorio tenemos. Entonces, éxitos en esta jornada. Muy buenos días.
Muchísimas gracias y nos vamos alistando, nos vamos preparando para nuestra conferencia, para nuestro encuentro internacional INFAS 2024. No sin antes darles a conocer a ustedes una pieza, una parte de lo que realizamos en Bienestar Universitario en la línea de cultura con el maestro Mauricio Carvajal. Escuchémoslo.
En la plena oscuridad, en las noches de mi llano, canta un carral. Yo no sé por qué será, pero lo noté cantando más lamentado. Sería que lo adivinó, que mi amor con otro amor se fue muy lejos. Si las cosas son así, carrito, hazme un favor, sé que eres bueno. Carrao, carrao, convida a tu compañero, al gallito lagunero, que lo salgan a buscar. Díganle que ya no aguanto, que entre el dolor y el llanto conmigo van a acabar. Díganle que no hay rencor, que le perdono su error, que regrese a mi lugar. Carrao, carrao, convida a tu compañero, al gallito lagunero, que lo salgan a buscar. Díganle que ya no aguanto, que entre el dolor y el llanto conmigo van a acabar. Díganle que no hay rencor, que le perdono su error, que regrese a mi lugar. Carrao, síguele la huella, que mi llano taciturno se enlutará. No brillarán las estrellas, ni la luna en plenilunio lo alumbrará. Y aunque tengo la esperanza que la última que muere, de que él regrese, Carrao, sigue tus andanzas, pregúntale si me quiere o me aborrece. Carrao, carrao, olvida a tu compañero, al gallito lagunero, que lo salgan a buscar. Díganle que ya no aguanto, que entre el dolor y el llanto conmigo van a acabar. Díganle que no hay rencor, que le perdono su error, que regrese a mi lugar. Carrao, carrao, olvida a tu compañero, al gallito lagunero, que lo salgan a buscar. Díganle que ya no aguanto, que entre el dolor y el llanto conmigo y a mi lugar. Muchas gracias.
Muchas gracias, maestro Mauricio Carvajal. No en vano fue uno de los boyacenses reconocidos en los premios Grammy con su agrupación Palo Cruzado en 2016. A ellos nuestro agradecimiento por acompañarnos en esta apertura. Invitamos entonces ya para comenzar al doctor Héctor Suárez, quien hará la presentación de nuestro conferencista internacional.
Buenos días. De verdad que para mí es un verdadero placer presentar a nuestro conferencista que va a hacer la charla inaugural, el doctor Samuel López. Él viene desde Porto, Portugal. Es matemático puro de la Universidad de Porto. Hizo su maestría y su doctorado en la Universidad de Wisconsin, Madison, en Estados Unidos. Su maestría la terminó en el año 2000 y el doctorado en el año 2003. Desde el año 2004 pertenece al Centro de Matemáticas, es un reconocido centro de investigación de la Universidad de Porto. De ese centro también fue director entre el año 2021 a 2023. Jurado evaluador de más de 15 tesis de doctorado, más de 30 tesis de maestría, revisor de artículos en más de 30 revistas, todas de reconocimiento internacional. Se destaca una de las que es nuestra revista de pronto más importante en el área de álgebra, que es Journal in Algebra, de muchas revistas, de cuartil Q1 y Q2. Ha hecho distintas visitas como investigador y como cooperador académico en varias universidades de distintos países, más de 15 países, entre ellos Estados Unidos, China, Argentina, Italia, Inglaterra, y bueno, ya puntos suspensivos y pronto aparecerá nuestra UPTC en Colombia. Trabaja también en proyectos, ha colaborado en el desarrollo de más de 12 proyectos, conferencista en más de 25 eventos internacionales en distintos países, conferencista también a nivel nacional allá en Portugal con más de 30 conferencias en distintos eventos. Director de tesis de doctorado, de maestría, bueno, puntos suspensivos. De verdad que es un honor para nosotros tenerlo acá. Bienvenido, profesor Samuel, a Colombia, bienvenido a la UPTC. Él nos va hoy a dar una charla que se titula Symmetric Throw, Representation Theory. Entonces, lo dejo con ustedes y espero que lo recibamos con un fuerte aplauso, profesor Samuel. Bienvenido a Colombia.
No sé si se puede dejar. Bueno, buenos días, muchas gracias y mucho gusto estar aquí en Colombia y muchas gracias por su presencia aquí. Yo quería agradecer primero el
Se acerca su merced al micrófono, para que lo puedan escuchar en la transmisión.
¿Cómo?
Que su merced se acerque al micrófono
okay.
para que lo escuchen también en la transmisión.
Sí, bueno. Yo voy a continuar a hablar en inglés si no se importan. So, it's a big pleasure, it's a great honor to be here. I'm very happy to be in Colombia for the first time and in Tunja. I have been extremely well received. I'm extremely honored by the possibility to give this opening lecture. And so I really thank the university, and in particular I'd like to thank Professor Héctor Suárez for the kind invitation and for making me feel very comfortable and for attending to all the needs that I have, and Dr. Judith for all her help through the process as well. So let's see, maybe I tend to be restless when I'm speaking, so I'd like to move around. Okay, so my talk is about symmetry through representation theory, and this conference is also dedicated, kind of the sub-theme is artificial intelligence. So my goal is to say a little bit about the role of artificial intelligence in mathematics, or the possible role that it can have through different aspects. I'm not an expert on this, but I'll tell you what I know. I also want to explain symmetry. Because I know this is a diverse audience, I'll try not to be very technical. So I'll try to explain symmetry, I will try to explain representation theory, and give you some flavor of the kinds of things that interest, that drive my work, that drive my research, without getting into very technical points. So before talking about AI, maybe I will start with symmetry and representation theory, because when I mention AI, at some point I will mention representation theory, so I prefer that you already know what I mean by this. So symmetry in general it's a very vast concept, and it's a concept that it's not only a mathematical concept. I mean, in this session we're more dedicated to physics, chemistry, biology, and mathematics, and certainly in all of these areas, symmetry has a very prominent role. I mean, anyone from this area, I think, will acknowledge this. Specifically, for example, well, in physics, this is completely undeniable. The principles of symmetry are the driving forces of the physical laws. And I will say a little bit more about this when I mention the physicist and mathematician Emmy Noether. In chemistry, this is certainly clear when you think of atomic connections and the formation of molecules and the symmetries that these have. These are important in this research. In biology, I don't know as much, but when I talk about mathematics and biology, I tend to focus on DNA. And in this particular topic, if you think about DNA folding and the way that it knots and the influence that this has, I mean, this is a manifestation of symmetry. So symmetry is extremely relevant. I would say that in my mind, symmetry goes much beyond science. And I've just came up with this concept as I was thinking about how I was going to talk about symmetry. But I would say, for example, what are the symmetries, for example, of myself? What are my symmetries? I would say that my symmetries are the acts that I can do, the transformations of myself, the things that I can do within myself, the ways that I can act, which do not change intrinsically the person that I am. So this would be symmetry for a human being. So symmetry, I think, is a completely universal thing, and this is how I think about it. Okay? So representation theory is a field of mathematics that I would say that all fields of mathematics ultimately deal with symmetry, but in a very specific way, representation theory is the field of mathematics which, per se, is more interested in symmetry. And it's also one of the fields of mathematics that most interacts with all of the areas of mathematics and other scientific areas, in particular mathematical physics. Okay? So what is representation theory? So one way to describe it is, and this is not my idea. I've stolen this idea, but I think it's a very good way of explaining it. Imagine you're a child psychologist. So if you're a psychologist and if you want to analyze a person, you will ask questions. You'll have the person sit on a couch and ask them questions about their childhood, about their experiences, potentially about certain traumas. But if you're a child psychologist, this doesn't work. You're not going to sit a child on a couch and ask them about their childhood or their traumas. So how do you analyze, how do you study the child from the psychological point of view? Well, you see how the child interacts with the world. You see how it interacts with other children. You see how it plays, how it interacts with objects, with toys, with adults, with animals, and so forth. And from understanding how the child is interacting with the world, you make inferences about the child. You try to understand the child from the point of view of how the child is interacting. And this is really representation theory. So representation theory is studying objects which can be abstract through the way that they interact with other spaces or other objects. Okay? So this is the point of view of representation theory, and this is why this is symmetry, because I'm studying the symmetries of an object in the sense that I described before when I told you about my symmetries, the things that the object can do, the operations that the object can do, which are intrinsic of the object. Okay? So this is representation theory. Of course, mathematically, this is a very informal way of saying it. Mathematically, this is something, a bit more precise, but this is the idea. So I think, although, as Professor Hector said, I'm a pure mathematician in the sense that I'm from the fundamental side of mathematics, and so I'm interested in abstract objects, but studying them through representation theory, I'm studying the way that they physically interact, for example. And this is one of the reasons why representation theory and physics are very connected. Okay? So, for example, if I think about, for example, if I have a deck of cards, and if I'm shuffling them, okay, this is an operation that's being done. The abstract object that's behind this operation is what we call a group in mathematics. But, for example, in physics, one usually only sees the representation of some abstract object. So, for example, for an abstract mathematician, I think of an abstract object and I think of what are the representations of this object. A physicist would think in precisely the reverse order. I have this, physical manifestation. So there's something that's acting here. Imagine that the child is invisible. You see that certain things are happening, and you're trying to think, okay, so there are these transformations, these things are happening. What could justify this? What's the structure behind this? And this is going backwards to the abstract object. So this is the kind of the interplay of representation theory, and so hopefully this gives you an idea. Okay. So now going into artificial intelligence. I'm going to speak about several aspects of the interplay between artificial intelligence and mathematics. So one, which is kind of more organizational or not administrative, but kind of strategic, is often mathematicians are sometimes, I think mathematics, maybe, so sorry to change slightly, this is something I wanted to say. So typically, I think, mathematics appears to be a challenge for artificial intelligence. Okay? I know I'm biased because I'm a mathematician, but the reason is mathematics tends to be extremely creative, and it tends to appeal a lot to intuition. And this is something that artificial intelligence has been having difficulties with. Okay? So the role of artificial intelligence in mathematics is still not very developed because of this. I mean, artificial intelligence, I've tried playing with artificial intelligence to prove something extremely simple in mathematics, a proof by induction, which is very simple, and it couldn't do it. And with more sophisticated systems, and I will talk a little bit about this, it can do a little bit more, but at a certain level, up to recently, artificial intelligence in mathematics could go up to high school mathematics. That's as far as what artificial intelligence could learn and could do and could replicate. Okay? Nowadays it's not. I mean, recently this has changed a little bit. So so for mathematics, this could be. I mean, we could think that we should set ourselves a little bit aside from this aspect. But I don't think we should do it. And in fact, when I was the director of my research center, the Mathematics Center of the University of Porto, we joined what's called an associated laboratory, which is really a consortium of several research centers in different areas, devoted to artificial intelligence. Okay, so this is this thing here called, which we call LASI. So it's called the Intelligent Systems Associate Laboratory. So a lot of my colleagues were kind of against this because they were saying, and they were right, I mean, we're fundamental scientists. What are we going to do in the group of, so the other laboratory, the other centers here are mostly dedicated to medicine, energy, and so forth. And they were saying, what can we do in a center like this? This is not for us. But I think, I mean, and still I don't regret this, I think we need to give this a chance, and we should not fall behind on these kinds of ideas. So we have integrated this center. We're the only mathematics group within this laboratory. As I said, the other researchers are from medicine, from energy, and so forth, planning, some engineering. And the goal is to use intelligent systems to make improvements on health, improvements on transportation, smart cities, even public service, okay, making better decisions, making better rules. And I'm hoping that, well, this will help us stay at the top of the iceberg in terms of research. So far, I must say, there haven't been too many interactions between us mathematicians and the other researchers in the other areas, but some have started, mostly taking advantage of a group we had, which was working on data mining and working on using mathematics within medicine, and so and also image processing. So the few mathematicians we had in these areas, and also in probability, could interact a little bit better, and so they approached the other centers in this laboratory, and something, not much has happened yet, but something is happening, and I'm hoping that this will be. I mean, I hope this is not my idea for the future of the Mathematics Center of the University of Porto, but I think this should be one of the aspects which should not be forgotten. So I think we must accept these challenges and see what we can do with them. So this is one aspect. Another aspect of artificial intelligence comes with a parallel with computation. So computation is not artificial intelligence, but 20 years ago, or maybe 50 years ago, computation power did not play the role that it does now in mathematics, especially in areas like numerical computation, numerical methods in solving partial differential equations and so forth. So having computational power has really enhanced research in mathematics. And so artificial intelligence can further this role and can go in this direction. And even fundamental mathematicians who had never used computational tools before, and I'm an example of this. I like to do everything on paper. I don't like calculators. I don't know the multiplication table, so I avoid all of these things. But even I sometimes use computational tools to explore a certain conjecture or to illustrate certain concepts. And so I think the same thing would happen with artificial intelligence. Okay. So another more meaningful aspect of this, and this is going to more success stories. And I know of these experiences. So there's this interface called ProverX, which is used by some colleagues of mine in Portugal, not at my university, but in Lisbon. And so this is kind of an interface which integrates a lot of things like GAP, Python, and so forth, and using artificial intelligence. And it's an extremely powerful tool to prove conjectures in certain areas of mathematics. So for example, one of my colleagues called João Araújo, he's a very good mathematician, working in algebra, so mostly discrete things, so things like graphs, semigroups, automata, things like this. He claims to have proved countably many conjectures using this kind of software. Okay, so the advantages of this software is that it's really powerful. I mean, as I said, I mean, he's proved a lot of open conjectures using it. The disadvantage is that it's very limited in its language. So it uses a very, I mean, the things that he can prove with the software, because of the things that he can kind of program into this type of platform, are limited to kind of discrete things like I explained, things related to graphs and automata and semigroups and monoids and things like this. Cool? See? Okay, yeah. Okay. So this is the disadvantage, okay? So for example, the famous conjectures in mathematics, the Riemann hypothesis, are completely beyond the scope of using software like this, okay? On a very different note, we have something else called Lean, which is another software. It has a different perspective. The idea is to, initially the idea was that it would be a proof checker, a software that it would check if a proof was correct or not, okay? Nowadays, it can go beyond this, and so some of you might have heard of this mathematician from Imperial College, Kevin Buzzard. He's one of the advocates of this. He uses this in his classes and at the Imperial College. And so the idea is first to create a platform that I can write a proof, and the software can check if my proof is correct. So the one big advantage of the software is that it's much more complex than the one that I showed you before. So you can make very complicated definitions, and you can introduce very, very, very complicated concepts into the system. In particular, for example, in algebraic geometry, very deep things. But the problem is that it's not so good at being creative and then proving things. Okay, but some things have changed. So at a certain point, it was able to solve problems at the level of a mathematical Olympiad for high school students, which it's not bad. Okay, but most recently, with more tools from artificial intelligence, it has been able to solve problems at the level of a silver medalist for an international mathematics Olympiad, which is something very, this is very demanding. Most mathematicians, I wouldn't be able to solve most international math Olympiad problems. They're extremely challenging. Okay, so this is a very promising thing. And in particular, well, maybe I won't be, I was going to mention a few more technical things, but maybe I won't. And I will give you now a very concrete success story, which is, there's this Australian mathematician called Geordie Williamson, and he's one of the mathematicians also interested in representation theory. He works in representation theory, and he has used artificial intelligence to develop his work, to the extent that, I mean, it's not normal that a pure mathematician publishes in Nature, but he has published in Nature on how artificial intelligence can help develop intuition for mathematical proofs. Okay, so let me be more specific. So there's this open conjecture, which I won't mention. It's called the Kazhdan-Lustig combinatorial invariance problem. It has to do with representation theory. Okay, it's an open conjecture. No one knows how to tackle it. He hasn't solved it yet. But what he has done is with a team of other people, not necessarily mathematicians, more on the learning side of things. So he has created systems that can learn about the patterns of these things that are conjectured, and using this, and as Dr. Judith mentioned, artificial intelligence is very good at finding patterns. Typically, we like to think of humans and mathematicians as the best at finding patterns, and we are extremely good. But now artificial intelligence can find certain patterns which we can't. And so they learned this system, and the system found some patterns. And these patterns are related to these polynomials, so it's hard to imagine for a non-mathematician that there's some open conjectures related to polynomials. And these are very nice polynomials with integer coefficients, okay? But so the system found that the calculation of these polynomials, most of it, so kind of the bigger part of the polynomial, depended on a certain thing, only on a certain thing, not on all of the information, but only on part of the information. So this enabled them to kind of find a way to a weak spot to kind of prove this conjecture. And they would not have found this without artificial intelligence, according to Jordi Williamson, okay? And I believe him. So ultimately what I'm saying is that artificial intelligence does play a role in mathematics, more than I would have suspected maybe a few years ago, because of thinking, well, artificial intelligence cannot be as creative as a mathematician, okay? And I still think that it cannot be as creative as a mathematician, but it can find patterns that we cannot. And this can help us solve more complicated problems, okay? So this is kind of my introduction, a large introduction. And maybe I will delve into human mathematics, okay? So there will be no artificial intelligence from the rest of the talk, okay? All the mathematics here on forth is human, okay? So two of the humans involved in what I'm going to say, in fact, because I don't want to get things to be technical, the part where the kind of the joint research with these two colleagues starts is probably the part where I'll stop my talk to avoid being too technical and to avoid tiring you too much. But okay, so these are two of my collaborators that inspired more or less this talk. One is Slava Futorny he was from Brazil, São Paulo, but he's currently in China at SUSTEC, a very, very high-level math center led by the Fields medalist Efim Zelmanov. And Eduardo Mendonça from Brazil, but currently at the University of Lyon, working with Olivier Mathieu, also a mathematician involved in representation theory. So these are the two collaborators that inspired kind of this talk. And another person who inspired this talk is a very wonderful mathematician called Georgia Bankart, who died before her time, unfortunately. She was my advisor. She was one of the most important advocates and most important mathematicians in the field of representation theory of all kinds. She was a wonderful person, and this work is dedicated to her. In fact, it's appearing in a special issue of Journal of Algebra dedicated to her memory. So this is the other human appearing in this talk. And so let me start with this idea, and let me start trying to tell you what motivates me, and how these ideas of symmetry and representation can influence what interests me. So in terms of algebra and geometry, we know that they have been hand in hand since the beginning. If you think of the unknown x, that was a measurement or an area or something like this. So geometry and algebra were always connected, but then they were further connected by Descartes when he introduced coordinate systems, and we can start associating to a point in space and to geometric objects. We can associate coordinates, and we can prove results in geometry using algebra, and we can prove results in algebra using geometry. But then there's a further connection between algebra and geometry, and this comes from the German mathematician Felix Klein in his Erlangen program, where he has a kind of a stronger and a deeper philosophy, which is the following. Studying geometries is the same thing as studying groups. In what sense? Well, first of all, for those of you who are not mathematicians, I think, physicists will know what a group is. I think chemists might too. Biologists, I don't know. So a group is essentially a set of transformations on a space, in such a way that any transformation can always be undone, and that will still be one of the admissible transformations. And if I do one transformation and I do another transformation, that is still one of the possible transformations, okay? So the examples that you should keep in mind is, one is shuffling, okay? I can always shuffle back if I remember what I've done, okay? And if I shuffle once and then I shuffle again, that's still shuffling, okay? So this is related with a group of permutations called a symmetric group. It's a finite group. It's one of the most important finite groups. And another example is matrices, which I think most of you in science have dealt with, okay? So if you think of invertible matrices, so matrices with non-zero determinant, this forms a group, okay? Because you multiply two invertible matrices and it's still an invertible matrix. Because it's invertible, you can always undo it. So this is another group called the general linear group, and it's one of the most important infinite groups that you can think of, okay? So this is what a group is. And so what's Felix Klein's idea? His idea is that, well, studying geometric objects is the same thing as studying the symmetries that remain valid for these geometric objects. Okay, so if I choose a group, the corresponding geometry will be the objects which do not change, which retain all of their properties after doing these transformations. For example, consider rigid motions in three-dimensional space, so kind of translations, rotations. If you consider that, I don't know if physicists consider a reflection a rigid motion, because I mean you'd need to go into higher dimensions the fourth dimension to realize a reflection. If you think of those as the transformations that interest you, as the group that's going to interest you, then the geometry that you get is Euclidean geometry. Because when you take a triangle and you translate it or you rotate it, it's still the same triangle. It has the same properties. So this is the idea between this is the idea behind this Erlangen program. Groups and geometries are more or less in correspondence, okay? So this is one aspect that I want to mention. From the physics point of view, I want to mention Emmy Noether, okay? A brilliant woman mathematician and a brilliant physicist. And she further showed that the existence of symmetries in a Hamiltonian system implies the preservation of some physical quantity. Okay, so specifically, for example, unfortunately, I mean, the two areas that fascinate me the most are geometry and physics. But unfortunately, I'm an ignorant in both. But at least I try to get some inspiration from both. But for example, this would say that, for example, preservation of energy is the consequence of the invariance of physical laws under time translation. So if a physical law is invariant under time translation, then energy should be preserved. And so this is Emmy Noether's idea. This was part of her PhD thesis. And so this relates symmetry with physics in a very tight way. Okay? So when I think of symmetry, the first thing that comes to my mind is the Platonic solids. Okay, they arose precisely. I think you know them, right? The cube, the tetrahedron, the dodecahedron, the octahedron, and the icosahedron. Okay, so these are the kind of the most symmetric three-dimensional polygons, and this concept of symmetry has been embedded in us for such a long time that, when they're discovered, they embodied the elements of the universe. So, for example, the cube represented Earth, okay, and there was water and there was fire. So these were the elements, okay. So this is our ancestors understood that symmetry was extremely important. So these are, for me, are the first examples that I think about when I think of symmetry. And so my next question is, okay, what symmetries do these objects have? Okay. Well, then, one good idea in science is to try to go a little bit above and try to, take a higher stance. And, well, I like to think that there's a sixth Platonic solid, which kind of contains them all, and that's the sphere, right? They're all inside of the sphere. They're all inscribed in the sphere. So first, I should think of, well, what are the symmetries of the sphere? Okay? If I think in terms of Euclidean symmetries, these are essentially the rotations. There's also the reflection. If you want, you can add a reflection, but that doesn't change much. Okay, so essentially the symmetries of the sphere are the rotations. So you choose an axis and you rotate along that axis. Okay, so those are the symmetries. And the group of symmetries has fancy name called SO3, which most physicists will know, possibly as SU2, which is not the same group, but it's related. It's the universal double cover, for those of you who know what that is, and SL2. So essentially, these three groups are, you can think of them as the symmetry groups of the sphere. These are infinite groups, okay? Well, the Platonic solids are kind of finite, so their symmetry groups are finite. So there will be subgroups of these. In particular, there will be subgroups of this group. So a natural question is, okay, what are the finite subgroups of this group here? Can I describe them? And do I get all of the symmetry groups of the, are there other groups which are not symmetry groups of the Platonic solids? So let's try to see. Well, these are the finite subgroups of this. I'll say by abusive language that they're the subgroups of the sphere when I mean that they're the subgroups of the symmetry group of the sphere. So these are the finite subgroups of the sphere. Let me try to explain them a little bit. So the first one is called the cyclic group. It's essentially rotation. So for example, the cyclic group with three elements, you do a rotation of 120 degrees, then you do it again, you have 240 degrees, you do it again, you get back to zero, to the identity, right? So this is what a cyclic group looks like a clock, right? Going back to, and this is the symmetry group of a polygon like this, thinking of rotations, okay? Another finite subgroup of the sphere is what's called the dihedral groups, and I like to think of them as symmetries of the prism. So in this prism, you can rotate it, but you can also flip it around, okay? So you have an additional symmetry. And then you have the symmetry group of the tetrahedron, which, it doesn't matter, it's an important group called the alternating group. You have the symmetry group of the cube and the octahedron, and the symmetry group of the dodecahedron and the icosahedron. And here comes another principle of symmetry. You will notice and you'll inquire, why do the cube and the octahedron have the same symmetry group? Is this telling me something about them? And it is. It's telling me that they're dual to each other. So look at the cube, put in a vertex at the middle of each face of the cube, and then connect the vertices if the corresponding faces are adjacent. And then you'll get the octahedron. And if you do the same procedure here, you'll get the cube. So symmetry will detect these dualities, okay? And the same thing with between the dodecahedron and the icosahedron. And it detects other things which I won't mention, but I mean, you can think, well, these are all possible ways of permuting four objects. So if this is the symmetry group of the cube, what are the four elements of the cube that are being permuted here? This raises a nice question, and this is again my goal. Symmetry gives you an entry point into things which are invisible. Okay? So the four natural things that the cube is permuting are not really visible here in this picture. I won't tell you what they are, you can ask me later, but they're not obvious from the picture. So looking at the symmetry group allows you to think of things which are not a priori the most obvious things. Okay? And this has been happening for a long time. I can give you a couple of examples. In physics, electromagnetism, in a certain sense, was discovered through symmetry because it was predicted using mathematics before it was tested, before it was experimentally proved. And for example, in chemistry, the fullerenes, this combination of carbon, they were predicted theoretically using principles of symmetry in mathematics of how these carbon things connect. So in principle, it was discovered that these things could exist, and it was only later that they were discovered. So symmetry is a way a way into the invisible. Okay, it gives us vision. Okay. Okay, very good. So we have this list of finite subgroups of the sphere. So you see that not all the finite subgroups of the sphere are symmetry groups of the Platonic solids. There are a couple other more. Okay, but then the other thing that maybe you could remark is I mean, what is this? What is this column here? A, N, D, N, E. Where do these letters come from? Okay, and maybe some of you have seen these letters. Well, I think we've all seen these letters, but these particular letters, which are kind of funny, you know, why are they classified using these letters? Some of you, maybe especially the physicists, have seen, besides the mathematicians, have seen these letters before. And they appear in the list of diagrams, which are the diagrams that classify, you know, mathematicians like to classify. They classify these very important groups called Lie groups. So Lie groups are these infinite groups, which besides being a group, they're also geometric objects. Okay, they have a shape. For example, look at the circle. Circle is clearly a geometric object. But it's also a group because if you think of the circle as complex numbers of length 1, they can be identified with rotation. So when you multiply two complex numbers, you add the arguments. So this is also a group. So it's at the same time a geometric object and a group. And this is called a Lie group. Lie groups are extremely important, especially in physics, but also in mathematics and many other areas. And the nice Lie groups are classified using these diagrams. There's an issue here because in my list you didn't see B and C, and you did not see F and G. But the reason is that these diagrams are kind of different because they have these arrows and these multiple edges. So if you forget about those, this is precisely the list of diagrams that you get in that classification before. So this creates a question. So there is a connection between these finite subgroups and these completely different infinite groups, which are these Lie groups. Okay, so what is the connection? Well, the fact is that this list of diagrams appears in many different places in mathematics, and another place where it appears is in geometry. And this is where I'm going, okay? So in geometry, these diagrams are used to classify something else, okay? And the something else is called a Kleinian singularity. It's a complicated name. Klein, you've seen the name Klein before, right? Felix Klein. But I will explain to you what these Kleinian singularities are. So think of a surface as a geometric object, right? A sphere, for example. But sometimes the surface sometimes the surface has a point where it's not very good, where it's not very smooth. Okay? Let me show you pictures before. Okay? These are Kleinian singularities. For example, look at this double cone. It's a nice surface, except there at this point when these two cones meet. And this is called a singularity because it's a point where it's not so nice. It's not smooth. Okay? So these Kleinian singularities are these. This is the list of Kleinian singularities. There are these images here, very pretty, and they all have in common the fact that they have this one point where they're not so good, which is called a singularity. But it's not a very bad singularity in the sense, for example, this cone, if I opened it a little bit, I would get kind of something like this, you know, without that point. I could kind of resolve this singularity and make it nicer. So they're singularities, but they're not bad singularities. So these are called Kleinian singularities. Oops, sorry. And they're also classified by the same list. So the new question arises is, what is the connection between this nice geometric object and these finite groups that we saw in the same list? They're being classified by the same thing. There must be some kind of a connection, okay? And in fact, there is a connection, and this is what starts motivating my research. We're almost getting to the point where, you know, this is beginning to give me ideas, okay? So the connection, this will be slightly technical, but hopefully not too technical, okay? So if I want to study something nice in 2 dimensions in the plane, one way of doing it is looking at coordinates. And when I look at coordinates, I look at the projection onto the first coordinate and the projection onto the second coordinate. So these are functions, okay? These 2 functions, projection onto the first and the second coordinate, generate a polynomial ring in 2 variables. Okay? So in a certain sense, from the point of view of algebraic geometry, of algebra and geometry of this connection, in a certain sense, studying geometric objects or certain kinds of geometric objects on the plane is the same thing as studying algebraic objects in the polynomial ring in 2 variables. Okay? So let me explain to you by example what the connection is between the group and the nice picture. Okay? So let's take the simplest one of those groups, which is this Z2. The Z2 is just a rotation by 180 degrees. Okay? It's rotating. So in terms of coordinates, this is what it's doing. It's taking the first coordinate into its negative and the second coordinate into its negative. And I can think, okay, well, what are the coordinates that do not change after I do this rotation? What is invariant? What remains after I do this, after I apply this transformation? Well, clearly, u squared remains invariant because if I'm replacing u by minus u squared doesn't change. V squared doesn't change either. And u times v doesn't change either. So these three things are clearly invariant, do not change under this transformation. And it turns out that anything else which is invariant can be written in terms of these three elements here. So what in mathematical language, this would say that the ring of invariance is generated by these three elements here. But the point is that these three elements are not completely independent. You'll notice that if you multiply this one by this one, you'll get the square of the third one. So essentially, this ring of invariance looks like you think of three indeterminates. Okay, in this case, y corresponds to this u times v, x is u squared, z is v squared, and they satisfy a certain relation. The relation is that the square of this one is equal to the product of these two, so you get this equation. And when you get an equation, you get a geometric image, you get a geometric object. Okay? Here, I should have done this, but sorry, I didn't. If I replace x by, for example, a minus b and z with a plus b, okay, which I can, then this equation becomes this equation here. X squared plus y squared is equal to z squared. And this equation is the equation of the cone. So what I've just explained, let me remind you, what I've just done is I started with a group which was classified as A1. I looked at the invariance under this group. This gave me an equation. I transformed the equation a little bit, and this equation gave me a picture. And this picture is the Kleinian singularity. And this is the correspondence between finite subgroups of the sphere and Kleinian singularities. And I think this is very beautiful. When you find a very unexpected connection between two things which seem to be very different, a finite group is a very abstract thing which is finite. A Kleinian singularity is a beautiful infinite image that has some problematic point. Okay, so this opens up new perspectives. Okay, and in particular, without being too technical, I'll say this very briefly, just for the one or two of you who might know what these things are. So groups have representations. In particular, they have irreducible representations, and these irreducible representations correspond to a basis in cohomology, which essentially studies differential forms. Okay. And a group also has conjugacy classes, like when you have a matrix and you change the basis, you get a conjugate of the matrix. It's the same thing. So a group has conjugacy classes, and the conjugacy classes corresponds to a basis in homology. And homology is the study of shapes in geometry. Okay? And a beautiful thing is that we know from the algebraic point of view that a group has as many irreducible representations as conjugacy classes. So the number of things here is the number of things here. And we also know, it's called Poincaré duality, that homology and cohomology also have a nice correspondence. So everything is tying together in a beautiful, beautiful way. And this is good. It opens new ideas, okay? And this is where I'm going to start talking a little bit about research, okay? So we need to expand a little bit and to go from groups to algebras. So what's the difference? Well, an algebra in a certain sense is, from the point of view of quantum physics, an algebra is kind of a quantization of a group, in a certain sense, in the following sense. I gave you as an example of a group invertible matrices. Okay? Invertible matrices, you can multiply them, but you cannot add them, because if you add two invertible matrices, then the result might not be invertible. Okay? But when you start adding, you get something which is not a group, but it's called an algebra. So in a group, you can only multiply. In an algebra, you can multiply, but you can also add. Okay, so that gives you an algebra. So a good example of an algebra is the set of all matrices, square matrices. You can add them and you can multiply them. Okay, not every matrix is invertible. That's the price to pay, but you get something which is a little bit bigger. Okay, and why do we want to do this? Because we want to consider transformations which might not be reversible. An example of a transformation which is not reversible is, for example, taking the derivative. If I told you that I had a function and the derivative of the function is equal to 1, you don't necessarily know what the function was. I mean, at the most, if the domain was connected, you can say, well, it's x plus some number, but I don't know what number that is. So this operation, like taking the derivative, is not necessarily reversible. And this is why we take an interest in algebras, because then we study these kinds of more general operations. Okay? So let's look at some examples. Again, motivation by geometry. We know that there's this correspondence between certain nice geometric objects and certain nice equations. And this is a deep connection which I'm not going to explore. It's a very classical and very, very deep connection. But this, from the algebraic point of view, puts the emphasis on the functions on the geometric object. Okay? And these functions, the nice functions are the polynomial functions. They're generated by these projections onto the first and onto the second coordinate. Okay? So if I look at these two projections, and instead of projections, I think about multiplication by x and multiplication by y. These two operators generate an algebra which is commutative, because multiplying by x and then multiplying by y is the same thing as first multiplying by y and then multiplying by x. So this generates a commutative algebra, which is the polynomial ring in two variables. And I'm doing this on purpose because the polynomial ring in two variables was key for this correspondence between finite subgroups of the sphere and these nice Kleinian singularities. Okay? So what I want to do next is deform this picture a little bit. So instead of considering multiplication by x and multiplication by y, what if I consider, for example, take polynomials in t and consider multiplication by t and derivative with respect to t. These are two operations. The difference is that these two operations do not commute. If I take a function, first multiply it by t and then take the derivative, it's not the same thing as to first take the derivative and then multiply it by t, because the product rule tells you otherwise. Okay? So these two operations do not commute, but they satisfy the Snath relation here. So the difference between doing first x and then y and doing first y and then x is equal to the identity transformation. Okay, the SWAN stands for the identity transformation. So now I have something which is not commutative, which is what I like. I'm a non-commutative person, okay? Because the world is not commutative, we all know. You know, when you start dressing up in the morning, you know it makes a difference what you put on first, right? If you change the order, then the end result will be very different, okay? So this is the relation between these two operators, and this is very striking because this is known in physics, or it's related to the Heisenberg uncertainty principle. And I cannot resist quoting Wolfgang Pauli in a letter to Heisenberg, where he says, so in quantum physics, then x and y should be replaced by momentum and position. And these two operations do not commute, which is very surprising. This is the kind of the foundation of quantum physics, okay? And so Wolfgang Pauli says that you can see the world with the pi, so p momentum, or you can look at it through the qi. But if you try to open both eyes at the same time, you go crazy. And going crazy means that these two operations do not commute, okay? This is paradoxical. So these two operations generate something very important, which is called the Weil algebra, which is kind of the algebra which is generated by these two operators, if you want, okay? But of course, you could do something different. Instead of doing derivatives, you could do integration, okay? And if you do that, you get something slightly different. The new relation becomes yx minus xy is equal to x squared. And this is a very nice relation. This is called the Jordan plane. It's kind of a non-commutative version of the two-dimensional plane. Okay, and so this is the game that we want to play. Okay, we want to imagine through algebra. We want to imagine things that we cannot see completely through geometry. What I'm saying is, I want to think about what could non-commutative geometry be. So commutative geometry, as I said before, studying objects on the plane is more or less the same thing as studying things in the polynomial ring in two variables. So when I deform this polynomial ring in two variables and I get a non-commutative algebra, I could think in philosophy that what's behind this non-commutative algebra is some kind of imaginary non-commutative geometry. So this is the point. Okay? So I will need to go into relations which are a little bit more complicated. Okay? And but you know, that's where the connection with my research starts, and it's also connected with the research of Professor Hector Suarez, because he's also interested in these types of things. So very briefly, well, motivated by things coming up in physics, there's groups of physicists looking at some variations of the logistic model and so forth, and they were coming up with these algebras which, you know, had certain kind of properties. So with a PhD student, we defined these algebras which we called quantum Heisenberg algebras, and essentially you think of three operators which do not commute, but I'm giving the rules, I'm giving you the rules to how one gets past the other. You know, when you move to the right, there's a price to pay. For example, here you have an h and an x. If you want to move the h to the right, you can, but then you have to replace h with a certain polynomial in h. For example, it could be x squared. And so this relation could mean h times x is equal to x times h squared. Okay? So this is the type of relation that you have. I'm not going to go very deep into this. Okay? And these, you know, these were defined by me and a student. We studied them extensively, and I'm going to give you examples. Every physicist knows about SL2. SL2 is related to the Lie group SL2 of 2x2 matrices of determinant 1. This is its Lie algebra, which is kind of vector fields in that group. And this Lie algebra is essentially generated by these three matrices, very simple matrices. Okay? And the operation is not the usual operation of matrix multiplication. You need to do a commutator. Okay? Which is this one times this one minus this one times this one. So these are the relations for this Lie algebra. Okay? When you look at all of these operations combined, you get an algebra which is called the enveloping algebra, which is precisely this algebra from the family that I defined. So the family that I defined depended on a scalar here, which in this case is 1, depended on a polynomial and on another polynomial. So this is the data that you need to build the enveloping algebra of SL2. Which, as I said, is a basic block in Lie theory. Another very important algebra is the Heisenberg algebra, Lie algebra. So going very fast, if you know it, you know it. And this Heisenberg algebra also appears in the family that we have discussed. And there's a quantization of this Heisenberg algebra, deformation of this Heisenberg algebra, which also appears in this family. Okay? And then the final example that I want to give you, because this is the most important one for what I was going to say next, is the following. So consider these relations here. Okay? This is very similar, if you remembered SL2, or if you already knew about SL2, this is very similar to the relations of SL2. The difference is that this g of h here should just be the polynomial h. Okay? But, well, this mathematician, Smith, S.P. Smith, defined these algebras, which appear in the family that I just defined. And why am I talking about them? I'm talking about them very briefly because of the following. We're going back to Kleinian singularities, but now in the non-commutative world. What is the idea behind this here? I'm going to replace, remember, the story before was finite group, looked at the invariance in the polynomial ring, and this gives me a geometric picture. What I'm going to do is I'm going to replace the polynomial ring with a Weil algebra. Okay? So I'm going to look at this here. For example, if the group is Zn, okay, you could think of it as complex numbers which are primitive nth roots of unity, or rotations of an angle of 2 pi over n. Okay? This finite group here will act on the phi algebra in this way. It multiplies the generated t by this root of unity. It multiplies the other generated by its inverse. And I can look at the invariance. Okay? When I look at the invariance, this is a non-commutative algebra. It's no longer in the commutative polynomial ring. It's in the Weil algebra. So this is non-commutative. But it's generated by these three elements. Okay? And if I try to describe this algebra, it's a non-commutative algebra, and what I find is that it can be obtained as a quotient of the Smith algebra, which I just discussed before. A quotient by a very nice element, Casimir element, that's the name of another physicist, so it should be important, okay? So the invariants are related to that Smith algebra. And so these would be the new Kleinian singularities in the non-commutative world. And this is, I mean, if you want to be a little bit technical, this is not completely an abstraction in the sense that this deformation is reasonable because, I mean, in algebra, when people are doing analysis, you always look at the highest degree term and, you know, get rid of the lowest degree terms. In algebra, we do this by doing a filtration, which is essentially the same thing. You get rid of the smaller things. So if in this non-commutative algebra, you get rid of the smaller things, you get precisely the commutative algebra that defines the Kleinian singularity. So up to smaller degree terms, these two things match, except that in the other case, they're non-commutative. So this is where the research would begin, and so this is where my co-authors would come in. I will spare you that, but I'll tell you what we did. We studied all of the representations of these algebras, and we find really nice properties for these representations, for the way that they interact, for, you know, the combinatorial structure that they have. And so this is, so if I want to summarize what I've shown you here is that having a lot of connections, having different perspectives will open up new lines of research, will open up new world. And here, the contribution is the following. I have this classical picture, which is the relationship between these finite groups and these geometric objects. What have we done? Well, we've changed a little bit the setup. I've changed the polynomial algebra into a non-commutative algebra, which is the Weil algebra, and I've played the same game. And I've obtained these very nice non-commutative algebras, which have very nice properties in terms of representation theory, which are really impactful in other areas of mathematics, which I will not discuss. So thank you very much. Here's an example of symmetry.
Bueno, muchísimas gracias, profesor Samuel. Las preguntas, si las quieren hacer en español, no hay problema, él también habla español. Entonces, vamos con las preguntas.
Thank you very much, Samuel, about your conference. In few words, what is the importance for the non-commutative algebra in the artificial intelligence?
I mean, the question, I'm sorry to this, the question is, what should be the importance of artificial intelligence in non-commutative algebra? The point is that non-commutative algebra is unavoidable. As I explained, our world is non-commutative, right? I mean, the order in which we do things will change the end result. And everything in physics which uses mathematics mostly uses non-commutative algebra. So I would say that the question is, what can artificial intelligence do for this non-commutative algebra? And an example is the example that I mentioned by that Australian mathematician, George Williamson, because those problems where he used artificial intelligence with those Kazdan-Lustig polynomials, those Kazdan-Lustig polynomials are connected to the representations of the Lie groups that I showed you there. And they're also related to certain kinds of finite groups called Coxeter groups, which are very geometric kinds of groups. So there, artificial intelligence played an important role. The role that mathematics could play, well, okay, this is, okay, that gave me an idea. Non-commutative algebra has an important role, could have an important role in artificial intelligence for the following point of view. From the most elementary side of artificial intelligence, you have matrices. I mean, machine learning, for example, is based on matrices, on very simple things. Matrices are non-commutative. Two matrices, I mean, if you multiply in an order and if you multiply them in a different order, they do not commute. So why is studying non-commutative algebra relevant to matrices? Well, one of the nicest things that we teach when we teach matrices is diagonalization, eigenvalues. And when we can diagonalize a matrix, we can solve a lot of problems. Everything becomes much nicer, right? Representation theory, from a certain point of view, could be a generalization of this, not to one matrix. So we teach our students how to diagonalize one matrix. But the real problem in real life is we have 10 matrices, well, we have much more than 10. We have a bunch of matrices, and we want to diagonalize them simultaneously. We want to find a basis of eigenvectors which are eigenvectors for each one of them. This is not possible in general, except if all of the matrices commute. And representation theory, in a certain sense, is a generalization of this problem of eigenvalues. Eigenvalues divide your matrix into very small blocks. If you have a 3 by 3 matrix, the eigenvalue will divide your matrix into 3 things, which are nice. Representation theory, when the matrices do not commute, if it's possible to divide them into 3 things, it will divide it into 3 things, but when it's not possible, it will divide it into the smallest possible number of things, okay? And so my point is, representation theory, in a certain sense, is going towards generalization of linear algebra from one matrix to many matrices. In particular, they could be infinite matrices. And this will have an impact on machine learning and artificial intelligence because that's the basis of how those systems work. So that could potentially have, I don't know.
More questions? Thank you very much, Profesor Samuel. Muchísimas gracias, Profesor Samuel. Entonces, un fuerte aplauso de agradecimiento por la excelente conferencia. En un minutico la profesora Judith le va a hacer entrega del diploma.
Bueno, damos un certificado al doctor Samuel López por la participación en el evento de International Mission of Faculty of Science, por participar como nuestro invitado especial.
Muchas gracias. ¿Lo podemos hacer acá?